In this example, we're going to continue to explore writing the time complexity function, and this one is going to be slightly more challenging. In particular, if we look at this, nothing seems out of the ordinary. We have a function that depends upon the parameter n, and we get one flop down here. But then as we begin to notice our indices, nothing strange about our first loop. It goes from 0 to n. But then j, the inner loop, goes from a value of I to a value of n. So the tricky part here is that the value of j will depend upon what the current value of I is. So our goal here is to describe the order of this and to use a recurrence relation for t of n to build the time complexity function. So you'll see that we'll actually benefit from writing a recurrence relation. All right, here we go. So we have an outer loop, and that outer loop is going to execute the body. It starts at 0, so it doesn't start at 1. If it went from 1 to n, it would be a total of n iterations. But because it starts at and includes 0, it's going to be n plus 1 more. So to think about it, if you went from 1 to 5, started counting at 1 and went from 1 to 5, it would be 1, 2, 3, 4, 5. That's 5 counts. If you start at 0, 0, 1, 2, 3, 4, 5 is actually 5 plus 1, or 6 counts. Now this loop right here, from j goes from I to n. The number of times that this is going to run, this is going to vary, right? Because it depends on what our current value of I is. But lo and behold, down here we see that this is always going to generate 2 flops, or require 2 flops, right? Because of the fact that there's one assignment and one arithmetic operator. Now we want to come back up here and take a look at t sub n. So what is our recurrence relation going to keep track of? Well, this recurrence relation for the time complexity, this will ultimately transform into t of n, the number of, but right now, the number of total operations, but right now define t sub n, this recurrence relation, to be define this to be the number of flops for n what do I want to call this? For an input of n. Okay, so what I mean by that is, first of all, if we look at T1, right? We're not going to give this an n value of 0 because that's just not going to be terribly interesting, but I suppose we could, right? We could say T0. All right, let's do that. T0. So that's the smallest that it can be, of course, because you can't go from 0 to -1, but it can go from 0 to 0. So what would happen in this case? Well, first of all, I would be assigned the value of 0, and because we're going from 0 to 0, this is only going to happen for one value of I. Then down here, we're going to go from the current value of I, which is 0, up to the value of n, which in this case is also 0, right? So let's plug in some numbers here. Well, this will be 0, and this will be 0, because that's what we're considering right now. And so since the current value of I is 0, j will also be equal to 0. And then it will do this, right? It will generate 2, I'll just say 2 flops. Okay, so there it generates 2 flops. It comes back. We've run out of j values because it goes from 0 to 0, so we can't advance j to 1. I goes from 0 to 0. We can't advance I. So this is going to require 2 flops. Now let's look at what T1 would look like. T1. So T1 would mean that we're assigning n the value of 1. All right, so that means I is going to have 2 values. It's going to have I equals 0 and I equals 1. But before it advances to I equals 1, it has to come down here and say, all right, if I is 0, then j is going to run from 0 to 1. So that means there's going to be a run for j equals 0 and a run for j equals 1. Okay, so that means there's going to be 2 flops here and 2 flops here. But it runs through those 2 values of j. Now it comes back up to the top and says, all right, well now we need to run I equals 1, and j goes from 1 to 1. That means that the only value of j that will be executed here will be j equals 1, because it goes from 1 to 1, so it'll only run that one time, and that's 2 more flops. So we get 2 plus 2 plus 2. I is now maxed out, therefore we have 2 plus 2 plus 2, that's equal to 6 flops. All right, what we're going to do is we're going to start to see a pattern here, and hopefully we'll see it by T2 or at most T3. So sometimes you need to do this a few times to see that pattern, because notice what we're trying to do is we're going to end up building a table for this recurrence relation, and maybe I'll just go ahead and start it so you can see where we're headed here. What we're going to do is we're going to say, okay, let's generate for different values of n, let's calculate the Tn. And so far we have n is equal to 0 and n is equal to 1. And the output will be t of 0 equals 2 and t of 1 equals 6. As we generate more terms here, this will be our recurrence relation, and we'll see if we can generate a function for it. So if now n is equal to 2, notice that I will run 0, 1, 2. It'll start at 0 as always. It'll do I equals 1 and it'll do I equals 2. Now when I is equal to 0, j will run from 0 to 2. So j equals 0, j equals 1, j equals 2. Notice that that is a total of 6 flops. Now I becomes 1. And then j goes from I to n. So it'll go from 1 to n, and that means it'll just run for j equals 1 and j equals 2. This will give us 2 flops and 2 flops here. And then for I equals 2, that means j will run from 2 to 2, which means j will only take on a value of 2. It'll carry out 2 flops and then comes back up to I, but I is now maxed out, and therefore the loop terminates. So how many flops did we go through here? We went 2, 4, 6, 8, 10, 12. All right, so that means that t of 2 is equal to 12. Now at this point, I think I see a pattern. Notice that for n equals 0, there is only one value of I with one flop. T1, there's 2 values of I. The first one has two iterations. The second one has 1 iteration. And then notice that here it's 3, 2, 1. So if we were to hypothesize of what would T4 look like, well, the hypothesis would be, if there really is a pattern here, my hypothesis would be that T4, that it's going to run 4 2 flops, 3 of 2 flops, 2 of 2 flops, and then 1 of 2 flops. And so if I had another column here of j equals 0 through 3, I'm sorry, not T4, we're going to do T3, then I would say it's going to run a total of 4 times 2 flops, 3 times 2 flops, 2 times 2 flops, and 1 times 2 flops. So I'm going to predict that this is going to, for T3, I'm going to predict that it's going to require a total of 20 flops. Because what I'm anticipating here is that for I equals 0, it'll run 4 2-flopped iterations, and that will give us the extra 8 that goes on here. So now let's see if this actually pans out. 0 to n, so n is 3, n is 3 here as well. I will therefore take on 0, 1, 2, and I equals 3, and then it will terminate the values of I. J will run from I to 3. When I is 0, J will run from 0 to 3. So this is where I was saying that it's going to run 4 iterations of 2 flops each. But then when I is 1, J is going to go from 1 to 3. J equals 1, j equals 2, j equals 3. Each of these requires 2 flops. And hopefully you're seeing the pattern now that now I is 2, j will go from 2 to 3. And notice that it's kind of has this triangular form that we always start at 0 and then go up to the maximum j, but then the values of j decrease by 1 each time until I is 3, and then j goes from 3 to 3. So j will only have a value of 3 here, 2 flops. And notice that that's 2, 4, 6, 8. There's our extra 8 that I was talking about, 10, 12, 14, 16, 18, 20. And we indeed have 20 flops. So that's very good. And now we have t of 3 equals 20. And now we might imagine that the next one will simply increase, not by 8, but it'll increase by 10. And we would anticipate that, and this will in fact be true, that this will have 30 total flops. All right, let's drop this into our software and write a recurrence relation for it. So I am using Desmos, and I'm going to insert a table. And in that table, I will place 0, 1, 2, 3, and 4. And so now we can just plug in the values of our table 2, 6, 12, 20. And we can, of course, take a look at these values, set our x-axis to go from, we'll just go -1 to 5, so we can see a little bit on either side. And then y will set to go from 0 to 31. Actually, maybe -1 to 31, so I can get the full picture. So you can see how this is increasing. Looks like it's concave up, so it looks like it's going to be some sort of quadratic or cubic. So what I can go ahead and do in a number of different ways is I can actually choose from here, depending on when you're viewing this video. This might be an option. We could try to do a linear regression, which of course doesn't look good. We need this to be 100% perfect, right? R squared is 0.9722. You can do a quadratic, and look at that. That gives us a perfect fit. R squared is equal to 1. Now, if you tried cubic, that would also be a perfect fit. You would just get a 0 for the coefficient of the x cubed term. If you're trying to do different regressions, remember you can, referencing the names of these columns, you can go y1, and then this little wiggle, tilde, ax squared plus bx, and actually these have to be x1s, because that's what the columns are called, and that will also give us the same results for a, b, and c. So we have that our function, our time complexity function, which I'll just refer to now as t of n, is equal to n squared plus 3n plus 2. And that, the order of that time complexity function is, of course, quadratic, which is the dominant term here. So we have a quadratic order. Now that's not surprising because we have a nested for loop, but really the exercise here is to think through and actually write the time complexity function itself. But now that we have our final answer, we could look at the differences 4, 6, 8, and 10. The differences are not constant. That means it's not linear. But if we look at the second differences, 2, 2, and 2, we have what's called a delta 2 constant recurrence relation, and that means that it is going to be a quadratic fit.